Hello, everyone. My name is Lopez. I'm a Colombian PhD student at Skolkovo Institute of Science and Technology in Moscow. And my talk today is about the topic empirical analysis of investment capacity in distribution grid. This work is done by myself, Alvaro Gonzalez, and Professor David Pozo. And okay, the content of this presentation is as follows. First, I want to make a short introduction of the problem, and then I want to state the formulation and also the mathematical model that we are using and how to model other variables of the system. And then what methods we are using and some results, experiments that we have carried out. And finally, the conclusion that we have obtained. So let's introduce. Okay. So everyone knows that the traditional power systems are constructed in an unidirectional way. So the delivery of energy is made from the generation centers to the demand centers. But now the distributed generation has driven a change in the current power system topology. The new power system have a bidirectional exchange of energy between the demand and the generation. And the idea and the first question that we want to answer is where we should place the DG units within the distribution. And of course, the decision of which node to connect the DG unit is according to some technical requirements and trying to optimize an objective point. And additionally, we want to answer a second question. The second question is how would be the size of this connected distributed generator? And as you can see here, this is a capacity problem for the system plan. How much capacity in what should I connect in the system? The question that we want to answer. And now let's talk a little bit about the problem state. So the distribution system is the final step in the delivery of electrical power and connects the transmission system to the individual consumers. In this world, we face this problem taking into account some uncertainties. The idea is to use historical data from a weather station and a power meter located at the feeder and create a database with early measurement of power demand with speed and solar radiation. As you can see here, the solution is what kind of technology we are using and also which one will be the node that we are connecting these DG units. We can now talk about the methodology and the approach used, and we can start talking about the scenario generation method. So we are using the K-means technique to group a collection of historical data. The idea here is to determine a scenario level with the info about the demand, solar radiation, and wind speed. And then we use a two-stage stochastic programming to formulate the problem of DG allocation. We have a first stage with investment decision, and this investment decision is considering three technologies: the photovoltaic, PV system, wind turbines, and conventional generator or small diesel generators. And the second stage is taking into account the uncertainty in the system. And okay, we have here the optimization model. We have a sketch. We have an objective function taking into account the investment decision. And also we have some constraint defining the investment cost, the operation and maintenance cost. We have the power balance constraint, and we have also some engineering limit, the voltage, maximum power delivery. And also we have some relaxation because we have a bilinear product in the apparent power equation. And finally, we have a budget. The budget constraint is defined here. And this problem, we want to analyze the quality and the stability of the solution. And our investment problem formulation can be described and compactly summarized as a classical two-stage stochastic program. So the vector here is representing the investment decision, and the vector UI here represents the operational decision at the second step. We can estimate the value of the lower bound using N replicas and we can also estimate the upper bound using a fixed value, denoted here as S with a hat. And also we can estimate the optimal solution gap, taking the difference between the upper bound and the lower bound in the different solution. And let's talk about the result that we obtain in the problem. So the solution for a realization is the DG units located in different nodes. And also we are taking some mix of different technology. For example, the PV units, the wind turbines, and the conventional generator. And now we are taking different number of scenarios. The results are as follows. This figure here shows the optimal solution from the estimated lower bound and estimated upper bound. We can see here that the lower bound varies with the number of scenarios generated. The results show that using a few scenarios here maybe can lead to a suboptimal solution, or maybe we can take some substantial error. We have here a huge area here. So also we can analyze what happened with the mix of the different technologies that we are considering. So as you can see here, with a few scenarios, with a small number of scenarios, the variability becomes higher. And with a high number of scenarios, the variability of the different technologies is smaller. So we can now analyze an in-sample stability and out-of-sample stability for the different number of scenarios. This figure shows the in-sample stability, and you can see here that this in-sample stability is improved when we increase the number of scenarios. And on the other hand, the out-of-sample stability is also improved when we are taking more scenarios in the system. And to calculate the out-of-sample stability, we will insert the fixed first state solution of the sample M. And then we calculate the N scenarios that representing the true distribution. Some conclusions for this work. So we show that the investment solution based on a few scenarios may lead to misestimate and can do some deviation from the true solution. And on the other hand, the representation of the stochasticity in scenarios may affect the quality of the solution. The idea from this problem is that we can conclude that the solution satisfies the criteria of the in-sample and out-sample stability when the number of scenarios generated surpasses the 1,000 data points for this particular distribution grid. Some future work we can in the future evaluate different scenarios generation technique, and also maybe include some storage device like electrical vehicles, and maybe we can implement some long time planning horizon. This is the final slide. So thank you so much for your time and the presentation. So any question, please, you can find us at this mail. This is the end of the presentation. Thank you so much.